Descend past 700 meters beneath the ocean surface, and you enter a world that sunlight never reaches. The pressure here exceeds 270 atmospheres, enough to crush most machines and every unprotected human body. The temperature hovers near 2 degrees Celsius. There is no dawn, no season, no shadow of a passing cloud. There is only cold black water stretching in every direction, and the slow rain of dead matter drifting down from the sunlit world far above. This is the midwater realm, one of the largest habitats on the planet, and for most of human history it was almost entirely unexplored. Then, in a beam of artificial light thrown by a submersible, something extraordinary happens. A small animal, no longer than a human thumb, swims into view. It is a worm, soft-bodied and segmented, its body rimmed with delicate paddles. As the light approaches, the worm reacts. From near its head, it releases a tiny fluid-filled sac. The sac drifts free, and then it ignites, not with fire, but with a cold, brilliant green glow that hangs in the water like a floating ember. For several seconds, this luminous globe burns in the darkness, a beacon in a place that has never known one. And in that instant, the worm is gone, propelled backward into the black, leaving its glowing decoy behind. Scientists call this creature the bomber worm, and its trick is one of the strangest survival strategies ever filmed in the deep sea. It carries as many as 8 of these bombs, arranged near its head like a magazine of living light. When threatened, it can deploy them one at a time, sacrificing a piece of itself to buy a heartbeat of escape. But why would a soft, defenseless worm invest in manufacturing light at all? What chemistry burns inside those sacs? And how did an animal evolve to throw glowing bombs at its enemies in a world of perpetual night? The answers begin not with the worm itself, but with the machines that first found it, prowling the abyss with cameras rolling in the deepest darkness on Earth. For centuries, the deep sea kept its secrets, because we simply could not go there. Nets dragged behind ships tore fragile animals apart, turning delicate creatures into unrecognizable pulp by the time they reached the surface. Soft-bodied swimmers, like the bomber worm, left almost no trace. To find them intact, science needed a different kind of eye. That eye arrived in the form of remotely operated vehicles, or ROVs. Tethered robots lowered thousands of meters on cables, carrying floodlights and high-definition cameras. Operated by pilots on the surface, these machines could hover motionless beside an animal the size of a peanut and record it in its natural home. Institutions like the Monterey Bay Aquarium Research Institute deployed vehicles such as Tiburon and Doc Ricketts, drifting through the mid-water column where no troll net could work cleanly. It was in this slow, patient exploration that the bomber worms appeared. In 2009, marine biologist Karen Osborne and her colleagues published a formal description of these animals in the journal Science. They placed them in a new genus, Swimma, meaning the swimmer, and documented several species. The name captured how they moved, rowing through open water with their fringing paddles rather than crawling on the seafloor like most of their relatives. Osborne's team had recorded the worms releasing their glowing sacs on camera, capturing behavior no one had ever confirmed before. Careful collection with the ROVs, suction samplers brought living specimens to the lab intact, allowing researchers to examine the bombs under a microscope. The reason these creatures had hidden for so long was now obvious. They lived in a vast, three-dimensional space, far from any solid surface, in numbers too sparse to encounter by chance. Only when robots could linger in the dark, matching the worms' gentle drift, did their existence become visible. The discovery reframed the midwater as a place of active, elaborate defense rather than empty void. But the true marvel lay in the weapons themselves. 8 small sacs, poised near the head, ready to detach and burn. To understand the bomber worm, we must look closely at those bombs, and at the precise moment they leave the body. Look closely at the front of a bomber worm, and you find a cluster of small, rounded structures set near its head, just behind the mouth. In the best-studied species, there are up to 8 of them, arranged in pairs like a compact arsenal carried on the body's shoulders. Each is a modified appendage, transparent and fluid-filled, roughly the size of a grain of rice. In the resting worm they sit quietly, unremarkable, giving no hint of what they can do. Everything changes when a threat arrives. When the worm is disturbed, jostled, or seized, it can release one of these sacs on demand. The bomb detaches cleanly from the body, a controlled sacrifice rather than an accidental wound. As it separates and floats free, it begins to glow, filling with a steady green light that lasts several seconds before slowly fading. Researchers watching in the laboratory recorded the effect again and again, a bright globe suspended in the water, while the worm itself vanished. The escape is as important as the bomb. The bomber worm is a capable swimmer, driving itself with the fringe of paddle-like parapodia that line its body. When it deploys a sac, it does not linger to watch. It turns and rows hard into the surrounding blackness, putting distance between itself and the glowing lure it has left behind. A predator's attention snaps to the light, the brightest thing in an otherwise featureless void, while the worm slips away unseen. The elegance lies in the trade. The worm gives up a piece of its own anatomy, a structure it spent energy building, in exchange for the few seconds it needs to disappear. It is a decoy made of living tissue, a distraction that costs the animal something real every time it is used. That raises an immediate question. What exactly produces the light inside these bombs? The glow is not reflected, not stored sunlight, not fire. It is manufactured by the worm's own chemistry, a biological reaction refined over evolutionary time. To understand the bomber worm's weapon, we must follow the light down to the level of molecules. The green light of the bomber worm's bombs is a form of bioluminescence, light produced by a living organism through chemistry rather than heat. Unlike a flame or a light bulb, it wastes almost no energy as warmth. It is called cold light, and in the deep sea it is astonishingly common. Scientists estimate that the majority of animals in the midwater column can produce light in some form, making bioluminescence perhaps the most widespread form of communication on the planet. The reaction at its heart is elegantly simple. A light-emitting molecule, known generally as luciferin, reacts with oxygen, and this reaction is controlled by an enzyme called luciferase. When the two combine in the presence of oxygen, the luciferin is chemically excited and then releases that energy as a photon, a single particle of light. Multiply this across countless molecules, and the result is a visible glow. There is no filament, no battery, only chemistry poised and waiting to fire. In the bomber worm, this reaction takes place inside the detached sacs, so the glow travels away from the animal that made it. Green is a deliberate choice, though not a conscious one. In the deep ocean, blue and green wavelengths travel farthest through seawater, while reds are absorbed almost immediately. Most deep-sea eyes are tuned to detect exactly these blue-green colors. A green light is therefore highly visible to the very predators the worm is trying to deceive, which is precisely the point. The worm's glow joins a vast catalog of deep-sea light makers. Anglerfish dangle luminous lures grown from modified fins. Comb jellies scatter rainbow light along their beating rows of cilia. Certain squid release glowing clouds instead of ink. The bomber worm belongs to this luminous economy, but its solution is distinctive, a light it can throw away and leave behind. Yet knowing the chemistry only deepens the mystery. Building a light-producing organ is expensive, and turning that organ into a detachable, sacrificial bomb is stranger still. Where did these structures come from? The answer lies in the worm's own body plan, an ordinary anatomy reshaped by millions of years of relentless pressure from the hunters in the dark. Evolution rarely invents from nothing. It borrows, modifies, and repurposes structures that already exist, reshaping old tools for new tasks. The bomber worm's glowing bombs are a striking example of this borrowing, and the clue lies in where they sit on the body and how they are built. When Karen Osborne's team examined the sacs, they concluded that these detachable bombs are most likely modified gills. In many segmented marine worms, the head region carries branchiae, feathery appendages that absorb oxygen from the surrounding water. In the ancestors of swimmer, structures like these once served that ordinary respiratory role. Over evolutionary time, in the lightless midwater, a portion of this anatomy was transformed. The appendages became simpler, rounder, filled with fluid, and equipped with the machinery to produce light and to detach on command. What began as a breathing structure became a weapon. The driving force behind such a transformation is selective pressure, the constant filtering of survivors from the doomed. In the open midwater, there is nowhere to hide. No rocks, no burrows, no crevices. Only endless water in which a soft, slow-moving worm is dangerously exposed. Any hereditary trait that improved the odds of surviving an attack would be favored, passed on to offspring, and refined generation after generation. A worm whose gill glowed slightly when disturbed, drawing a predator's eye for even an instant, might escape more often than one that did not. Across millions of years, that small advantage could be sculpted into a full deployable arsenal of 8 bombs. This is evolution answering a specific problem, relentless predation in a place without cover with a specific solution, a distraction that can be thrown away. The bomber worm did not choose to sacrifice its gills. Natural selection simply favored those individuals whose anatomy happened to buy them seconds of escape, until the ability became standard equipment. But there is a catch. A weapon you throw away is a weapon you no longer have. A worm that spends all 8 bombs is defenseless against the next attack. Survival in the abyss depends not only on deploying the bombs, but on the remarkable ability to grow them back. A bomber worm that has thrown its light is a worm diminished. Each of the 8 sacs represents an investment of tissue, chemistry, and time, and when one detaches and drifts away glowing, it does not return. The worm must build another from nothing. This is the quiet cost of the defense, the price paid for every escape into the black water below 700 meters. Regeneration in these animals begins at the segment where the sac once anchored, near the head. The worm redirects cellular machinery toward the wound, laying down new tissue much as it would repair a torn body wall. Over days, sometimes longer, a fresh, fluid-filled sac swells into place, ready to be charged with the compounds that produce green light. Karen Osborne, who described the genus Swimma in 2009, noted that different individuals carried different numbers of intact bombs, from a full set of 8 down to a scattered few. That variation is a record written on the body. A worm with only 3 sacs has recently survived 3 separate encounters, or 1 prolonged assault. The arsenal is a ledger of danger already faced. Rebuilding is not free. Every calorie spent regrowing a bomb is a calorie not spent on swimming, feeding, or reproducing, and in the food-poor midwater, calories are scarce. A worm drifting a kilometer or more beneath the surface lives on a thin rain of marine snow, the slow fall of dead matter from far above. To manufacture bioluminescent sacs from such meager rations demands careful metabolic accounting. The timing matters too. A worm that has just thrown its last bomb is briefly defenseless, its brightest weapon spent, its replacement still forming. In those hours, it must rely on darkness alone, on the sheer difficulty of being found in a realm without walls or floor within reach. Survival becomes a race between the predator's next approach and the worm's slow rebuilding. And that raises the harder question. All this cost, all this careful regeneration, is directed at one audience: the creatures that hunt in the deep. To understand why the bombs work, we must meet the hunters they are meant to fool. The midwater realm below 700 meters is not empty, it is patrolled. Here live the predators that shaped the bomber worm's entire defensive strategy, animals adapted to a world with no sunlight, no landmarks, and almost nothing to eat. In this environment, hunger is the ruling force, and any signal of food commands attention. The hunters come in many forms. Bristlemouth fishes, among the most abundant vertebrates on Earth, drift through these depths in vast numbers. Dragonfishes hang motionless, jaws lined with needle teeth, waiting. Larger squid and gelatinous predators move through the same dark corridors. Most share a crucial trait: eyes tuned to detect the faintest points of light against absolute blackness. In the deep sea, light almost always means one of two things. It means prey, or it means a mate. Many midwater animals produce their own bioluminescence, and predators have learned across evolutionary time that a sudden glow is worth investigating. That instinct, honed by millions of years of profit, is exactly what the bomber worm exploits. When a sac detaches and bursts into green light, it triggers the hunter's deepest expectation. Something living, something edible, hangs in the water. The predator turns toward the glow. Its attention locks onto the drifting light rather than the worm now beating away into darkness. The trick works precisely because it uses the hunter's own biology against it. A creature starved in a barren ocean cannot afford to ignore light. Investigating costs a few seconds. Ignoring might mean missing the only meal in days. The bomber worm bets on that arithmetic every time it releases a bomb, wagering that hunger will override caution. There is elegance in this exploitation. The worm does not fight, does not flee faster than its pursuer, does not hide behind cover that does not exist. It simply offers the predator something more compelling than itself, a false promise glowing in the void. But predators are not machines. They possess nervous systems, capable of change. And so the question sharpens into something that decides whether the whole strategy endures. Can a hunter fooled once learn never to be fooled again? A decoy is only useful if it keeps working. If the predators of the deep learn to ignore the green glow after a single trick, the bomber worm's 8 bombs would become worthless within a lifetime, and evolution would abandon them. So the survival of the strategy hinges on a stubborn question: do the hunters ever catch on? The honest answer is that no one has watched long enough to be certain. Observations by remotely operated vehicles capture moments, not the accumulated experience of an individual fish over months. But the biology offers strong clues. Many midwater predators are short-lived and encounter countless luminous signals across their existence. Distinguishing a genuine glowing prey item from a worm's decoy in the split second an attack allows may be nearly impossible. The light looks like food because it is built to look like food. Learning also requires memory and repeated experience, and in the vast, sparse, deep sea, a single predator may meet a bomber worm only rarely. There may simply not be enough encounters for any individual to build an aversion. Each attack feels, to the hunter, like a fresh opportunity rather than a repeated con. This is the shape of an evolutionary arms race played across immense time. If predators ever began to distinguish decoy from prey, selection would favor worms whose bombs glowed more convincingly, or in patterns closer to real prey. The pressure would push both sides forward, hunter and hunted refining their signals and their skepticism in slow lockstep over millions of years. The genus Swima, described only in 2009, still holds most of these answers in reserve. We know the bombs exist, that they detach, that they burst into light, and that the worm escapes. Whether the trick fools a naive fish once, or the same fish 100 times remains beyond our instruments, for now. What is certain is that the strategy has persisted long enough to spread across an entire group of worms. That persistence points toward a larger truth, one written not in a single species but across the whole luminous fabric of the abyss. The bomber worm is not alone. It belongs to the genus Swima, a group of swimming worms discovered in the deep Pacific and beyond, each carrying its own arrangement of detachable glowing sacs. Karen Osborne and her colleagues named several species when they described the group in 2009, revealing not a single oddity but a whole radiation of light-throwing animals living below 700 meters. Together they hint at how common this solution has become in the dark. Zoom outward, and the bomber worm's green flash is one signal among countless others. The midwater ocean, the largest habitat on the planet, pulses with bioluminescence. Bristlemouths glow along their bellies. Jellyfish trail luminous streaks. Squid flash counter-illumination to erase their own shadows. Some estimates suggest that the majority of animals in the deep sea produce light of their own. In this realm without sun, life has learned to make its own. Light here is a language with many meanings. It lures prey toward waiting jaws. It confuses attackers. It signals to mates across the emptiness. It disguises a body against the faint glow of the surface far above. The bomber worm speaks one dialect of this language, using light not to hunt or to court, but purely to escape, converting its own tissue into a glowing sacrifice thrown to a hungry pursuer. This is the deeper lesson of the abyss. In a world of relentless predation, scarce food, and total darkness, evolution has turned again and again to the same tool. A soft-bodied worm with no armor, no speed, and no hiding place survives by manufacturing brilliance, by giving the darkness something to chase that is not itself. 8 fluid-filled bombs, regrown after every use, stand between it and the jaws that patrol the black water. From the first startling flash filmed by a robot's camera to the whole luminous ecology surrounding it, the bomber worm tells a single story about life in the deepest reaches of the sea. Where there is no sun, where hunger never sleeps, and where a moment of misdirection means another day alive, one principle governs everything. In the dark, light is survival.